Okay, let's go. All right. So, a few questions about the homework came up today in office hours. One thing is, how close should your answers be? One question. We'll answer. So uh, the person said that they got about 20 or 30% on the first poll. That sounds pretty reasonable. I think 20 or 30% relative to spice is pretty good. Second poll, they're off by a factor of 10. That's not so good. Okay, so we kind of chased down probably where the problem was coming from. When you put in your put in your transistors now, you've got to put in fact, I think I did this in notes. Here it is, right here. I'm pretty sure it's the same syntax as this. You need to put in area of the source, area of the drain, perimeter of the source, and perimeter of the drain. Okay? If you don't put those numbers in, then your transistor, it's like it doesn't have any source or drain, or there's some very small default value. And so your transistors will work very, very fast. Okay, so you have to include these values here. The gate capacitance, so these are all used for the parasitic drain and source capacitances, right? The gate capacitance is calculated from the W over L itself, right? So that you'll get the gate capacitance correctly, but what you won't get is these little junction capacitances on the source and drain, okay, that are pretty important when you talk about like that inverter output stage that you have. So so they come into the calculation here as we showed in the notes last time. Okay, so that's point one. When you look at the results of SPICE, they'll give you a bunch of poles and zeros where the pole and zero are almost exactly the same point. You know, there'll be 1 plus, let me just write this down, omega z, and this is what a transfer function would look like, right? J omega over omega p. You know, and plus all sorts of other ones, omega p. Notice if omega p equals to omega z, okay, then these two terms will cancel out. Okay, what SPICE will do, it's calculating the roots of these polynomials to the best job it can through its little algorithm inside there for root solving. But there's some error at which it will declare that it has found a different zero and a pole. Okay, and so it'll show up. But in fact, if they're just very close to each other, within a very much fraction of percent, these coupled poles and zeros will have no effect on your transfer function, right? So effectively look at the poles and zero lists, and any pole that's about the same as a zero, just cancel those out because they're not important. Okay, it's just coming from this finite accuracy of the SPICE root solver. Okay, so that's another point. Anything else? I guess that was it. Any other questions or anything? Homework? Homework's due Friday. New project will come out. Okay. What I'm going to do today is just basically frequency response. So I'll just kind of go through one more topic and then just kind of review frequency response issues until we get tired. Okay. So one final, it's actually a fairly useful technique. It's for calculating the lowest frequency pole. Okay. So it kind of stems from, if we write down our transfer function, it's called the zero value time constant analysis approach. Okay, it's only good for poles, and it's only good for the lowest frequency one. And so here's what effectively it relies on. Let's do 3 poles. Let's say a system has 3 poles in it. Okay, so here's a 3-pole transfer function. There's some DC gain in it. Okay, if we multiply this out, we end up with something that looks like this: 1 plus the first order term, which is j omega, times 1 over omega p1 n plus j omega squared, and so on. Okay? Now, if it's true, well, let me just do a couple of these here. This is 1 over omega p1, omega p2, right, plus 1 over omega p1, omega p3, plus dot, dot, dot. Okay? Now, what we're saying is if the poles are widely spaced, okay, and let's say what's going to happen is that, and let's say we're looking at, say, near the, well, there's a widely spaced. Let's say omega p1 is the lowest frequency pole. Okay, so omega p is much, much less than omega p2 and omega p3. Okay. That means that omega over omega p1 will be much, much greater than omega over omega p2 or omega over omega p3. Similarly, and if we look at what we have here, where there's the second order terms and any higher order terms, or the cubic term, I guess, you have omega squared over omega, let's look at this one, omega p1, omega p3, okay, and this, of course, is equal to omega over omega p1 and omega over omega p2, I guess, right? This says 2 here, right? So now if we have omega that's in the range of omega p1, so we're looking, let's say this is where omega p1 is. We're looking sort of we're interested in frequencies at omega p1 and below. So we're looking at the lowest frequency pole. You can sort of see that this factor here is going to be very small compared to this one. Okay. Okay, even though this may be near unity, this is going to be very small. So that'll make all these terms small relative to these terms, okay, because you always got one term that's really small. And since omega, omega p2, omega over omega p3 are much smaller than omega over omega p1, these are all small. So we can argue that what you end up with in a multipole response, okay, is just, the lowest frequency pole will be important. But now, that may be hard to calculate sometime. We don't know where exactly it is. So what happens if we just sum all the poles together? Take 1 over omega p1 plus 1 over omega p2 plus 1 over omega p3. If the poles are widely separated, this sum will end up being approximately equal to 1 over omega p1. So all the higher order terms aren't important, all the other terms aren't important, so we'll end up with something that's, by just summing the inverse of all the pole locations, we'll end up with something that's pretty close to the dominant pole, the lowest frequency pole. We call the lowest frequency pole the dominant pole. It's the first one we hit, and you'll see why we refer to it being dominant a little bit later on. So this is kind of a little crude argument why if you take the inverse of all the frequencies, all the pole frequencies, you'll end up with a good approximation to the dominant lowest frequency pole. There's actually a much more sophisticated way to come up with the same result, okay? And I think Gray and Meyer has it in there. I don't know if Rosavi does as well. There's some circuit theory way to get the same answer. The question is, how do you get, I'll use the results of that just for a second. How do we get this approximation to the sum of poles? Okay. That's what zero value time constant analysis is. Effectively what it's doing is it's calculating each of the capacitors. Let's say each capacitor, it could be true that each capacitor gives rise to a separate pole. It doesn't necessarily have to be true. I mean, you could clearly see a case where you have two capacitors and zeros, a resistor like this, right? And you can see that there's two capacitors here, but it's not two poles. Okay, so it's not necessarily true that each capacitor gives rise to a separate pole. But it kind of works out in the same, what we're going to see here is, because we're working here with inverse of the pole locations, really what we have here, omega p1, effectively is 1 over RC, so omega p1 inverse is equal to RC, so it's equal to the time constants. You can sort of see that if we have situations like this, if we're adding up the inverse of the the time constants or the inverse of the pole locations, it won't matter, right? I mean, this is RC1 and omega P2 would be equal to RC2. We add these two things together, right? Omega P1 inverse plus omega P2 inverse. It's going to be equal to R times C1 plus C2. So, a couple things going on here. By taking each capacitor individually, finding the resistance driving it, summing up all these time constants together, and if under the assumption that one pole is dominant, we can get an approximation to the lowest frequency pole. So you get that? So that's basically the zero time constant analysis approach. Okay? So it's a cookbook. Okay? Set all caps to 0 except for the one of interest. We'll do this for every capacitor. Find the resistance seen by that capacitor. In other words, I'll start off with this one. I'll set all the other ones to 0, so I just get rid of that one. I find the resistance seen by that capacitor. What do I mean by that? What I mean is take, for this case right here, take all the independent sources to 0, put in my little test voltage or test current, find the test current or test voltage, and figure out what resistance we have driving that capacitance. So you're looking from the point of view of the capacitor. Well, for this case, it's pretty obvious. What happens, you might often have another capacitor or another resistor on the other side. Okay, so you have to sort of look at the voltage across, or the current coming out of this driven by this voltage here, or vice versa. I mean, you can do the same thing, right? You can have a current here. Then you got to figure out the voltage across this current. Right? And of course, the answer is, once you figure this out, it's the same as the sum of these two resistors, right? Now, this is pretty straightforward. Where it gets even more complicated is if we have some dependent sources, because we're going to have some capacitors in places where they're going to affect the dependent sources. And I'll give you an example of that in a second. But so it makes it a little more complicated. But basically, all you need to do is to take the capacitor, replace it with our little test voltage or test current, find the effective resistance being driven by where that capacitor was. So you sort of look from both ends of where the capacitor is. And that gives you the resistance. So find the resistance seen by CI. That's what that means. We'll call that RI. Calculate the time constant associated with every one of those capacitors. Calculate all of the RI, CI. Then sum up that sum of time constants, take 1 over that, and you have the approximation to the lowest frequency pole, to the 3 dB. There'll be other ones, but we're calculating the lowest frequency one. Okay, so there it is. That's the zero time constant method. What's nice about it is you don't have to think too much, right? This is one of those things that's really good late in the morning, right? So you kind of just go in there, replace capacitors, and find resistances. Yeah.
So if you're just summing up all the RCs, why does it matter if one's dominant if you're just using the omega?
Why does it matter?
If you're assuming that one's dominant, why can't you just use that? Just find the one with like the biggest RC anyway.
So okay. So the answer is, well, why do all this stuff? Why calculate all these extra things? Why not just go for the one that's the biggest? Yeah. The question is, which one is it? How do you figure out which is the most important one? Okay, and that's what's not so easy to figure out. Okay, this is a way not so you don't have to think, right? Trying for something that you really like, right? The strategy is, I can do something and figure out the lowest frequency pole and just go through this little calculation, and I'll calculate the lowest frequency pole.
If you're going through and calculating the RC for every one of them anyway, when you find it, why do you have to sum it up in the end? That's extra.
Because you're going to find the one that's, well, maybe you have a situation like this, right? So you need to add them all up because you may have a case where you have two capacitors may be contributing to the same pole, right? So these may be on the same order. So you wanted to sort of take care of that case. But actually, you've hit the right answer here. This helps you a lot to figure out where probably the lowest frequency pole is. Okay? It doesn't, doing this little test here doesn't, it's not a direct translation to the lowest frequency poles. But if you find one node, one capacitor, and all of a sudden that capacitor has a huge time constant associated with it, wow, that's probably where the lowest frequency pole is. Okay? And you've heard me actually use this result, right? When I start looking at these time constants, I say look at the output resistance of this node, look at the capacitance of that node, look at the RC, that's the time constant, and I say, if that's really big, that's probably an interesting pole. That's probably, and so this is kind of a little bit of the math behind that approach to getting an estimate of where the worst pole is, the lowest frequency pole is. Right? So, makes sense? So, in some sense, I'm agreeing with you. I mean, you're right. I mean, if you look around, you find a bunch of them are really small, or you can look at it and see it's 1 over GM there. Yeah, just forget that one. It's not going to be the dominant pole for sure, right? You look around and find where the big ones are, and you find this one node is really big. That's, for a design, that's probably where you're going to go after and try to get that node have a smaller time constant, which means a smaller resistor and a smaller capacitor, right? Both parts of it. Okay, any other questions about that? Okay, so let's do it for a simple case. Let's do it for a source follower. Okay, ZV, 0 voltage time constant with a source follower. Okay, so here is our gate to drain capacitance, gate to bulk capacitance, and gate to source capacitance. So the 3 basic capacitors, okay? And a source to bulk capacitor. So this has got all the capacitors associated with it, okay? This can get pretty messy if we try to solve this small signal circuit directly, okay? But let's simplify this as much as we can. Okay, the first thing we notice is that CGD is in parallel with CGB. They both go from this node to ground, because this is an AC ground. Okay, so the gate capacitance, CG, I'll call it, is CGD plus CGB, so I'll just lump those two together. I have a CGS in this small signal model, which goes between the gate and the source. So here's the gate and the source. So this is the source here. Here's the drain. Here's the gate. Okay. There's a CSB, which is going from the source to ground. And so that's this one right here. So that's source to ground, the CSB. So here's our small signal circuit. Now we can go into this and take each one of these capacitors and find out the resistance that's driving it. Okay? So let's start off with CG. Okay, so I call it C1, but let's say CG. So we take CG, which is this capacitor right here, set all the other capacitors to 0. So we set this to 0, we set this to 0. If we do those two to 0, what do we end up with? This node is not connected to anything, right? So we simply just have R in, and that's capacitor. So that's the circuit right here. So as soon as we get rid of this CGS thing, there's no connection into the rest of the circuit. So we can put a little test voltage, find out resistance, it's Rn. Okay, so that's pretty easy. Let's do C2. C2 was CSB. Okay. CSB is the capacitor here, so we set all the other ones to 0. We get this circuit right here. Now, this is a little more complicated, right? Because, let's see here. Did I do this one? Oh, no, it's not very complicated, right? So this set all the independent sources to 0. This is VG. Okay. So, oh, whoops. Okay. So this is VG. Okay. This is set to ground. So this is GM times VGS, right? GM times VGS. But VGS is equal to 0 minus V out. Okay. So we have 0 minus V out through a dependent source connected to this node. Okay. And what's the answer to that one? We can do that right away, right? This is a dependent source dependent on the voltage across it. And if we change the polarity of this, right, make this in this direction and get rid of that sign there. So this is just simply 1 over GM in parallel with RS. So the resistance of this is RS in parallel with 1 over GM. Okay, so that's 2 down. This third one's even nastier. Okay, so this third one, what we do is we put a test voltage across where this, it's CGS now. Put the test voltage across that, okay, and calculate what IT is. And what's IT going to be? Well, we can calculate, I guess I'm forcing an IT, so we can figure out what the voltage on this side is. It's going to be Rn times IT. That's the voltage drop across this side. Right? The voltage on this side is going to have to be, we'll have to sum these two currents together, right? So this current through here, so let's call IRS is going to be equal to minus IT plus GM times VG minus V out, right? VG we said is equal to Rn times IT. V out is equal to IRS times RS. So I can substitute these two things into this. I can solve, and I end up getting VT. And VT, of course, is equal to VG minus VS. So I can find, which is IN RT times this. Solve all that, and I end up with R3, okay, which is R0 over Rn plus 1 plus GMRS, okay? And R0 is equal to RS in parallel with 1 over GM. So just solving this little problem right here. So I take the three time constants I just calculated, put them all together, and I end up with this is my answer, okay? And is there any more pages? Is that all I did? Okay, well, I guess we can look at this. So what do we end up with here? Let's go back to our original circuit. Okay. So here's the answer. 1 over Rn times Cg. So here's Rn times Cg, and that was Cgb plus Cgd. So that's kind of the input capacitance seen here. Okay. There's an R out. Okay, the R out was equal to, remember, R out is equal to 1 over Gm in parallel with Rs. So that's kind of the capacitance on the output here. So it's the resistance on this node, and you see CSB. Okay, so it's 1 over Gm looking up and Rs down in parallel with it with CSB. So that's that time constant. And this third one here we just calculated is R0 times CGS. So that's a little bit like the output resistance driving CGS. And this term right here, if you look at it, Rn over 1 plus GMRS times CGS, if you remember that, that's basically the Miller effect what we see with CGS. I mean, CGS is reduced in size. Right? Remember we saw this? This is Rn. Okay. So we have an Rn, and this CGS here, this is V out. This is CGS. The C Miller here is equal to CGS times 1 minus GMRS over 1 plus GMRS. That's the gain of a source follower. Okay. And this thing right here ends up to be just simply 1 over Rn over 1 plus GMRS. So this is just the old Miller multiplication thing. It falls out. Okay. So it's all the possible poles just all added together. Okay. One of them's dominant. You can look and try to see, is this the dominant one? Is this the dominant one? Or is this part here the dominant one? Okay. And you can sort of figure out, which of the nodes you need to sort of work on to increase the frequency response of the circuit. That's it. So that's zero time constant analysis. It can work for a very complex circuit. I think the real insight to get from this thing is this idea of time constants, right? The idea that you have a capacitor, you find the resistance driving that capacitor, and that is a part of what sets the dominant pole. What about the second pole? Unfortunately, as we're going to learn in a few weeks, a month, it turns out for stability, the first pole, what we'll do is make it to be very low frequency, so we can make the circuit stable. It turns out it's the second pole, which is actually the really important one for setting our frequency response. In fact, we'll have to fool around with the first pole depending on where the second pole is. So it turns out what you really need to calculate is the first two poles. This tells you nothing about the second pole, the next highest one. That's just the way it is. And there is no equivalent, there's no little trick to figure out how to find the second one. I mean, you could sort of look at these time constants and get some insights into it, but certainly the summing up here doesn't help you in that at all. Right? So this is only for the lowest frequency pole, and its insight it gives you. So any question about
that? Can you just say why we need the first two poles? Why is it important? You said we only care about the first two.
Yeah, it's because of the stability thing. Remember I told you the basic problem is this. Okay, we'll have negative feedback. The problem we talked about was when do we get in trouble? So when this becomes a plus and that becomes a minus, we have positive feedback. That's the stability problem. When do we get, how many poles do we need to have to turn from a minus to a plus for the first time? Right? We get 90 degrees, minus 90 degrees of phase shift from the first pole. We get at 10 times above the second pole, we get another 90 degrees of phase shift, so we get 180 degrees. So after we go 10 times above the second pole, that's when we first hit this minus 180 degrees of phase shift. That's when we become unstable. So you need to look at where these first two poles are to be able to figure out the stability problem. There'll be more poles out here, but you're already toast, right? Because once you go from negative feedback to positive feedback, you're unstable. So it's the first two poles that give you the trouble. Okie doke. All right. Any question about
that? For the second pole, can we just add all the time constants except for the first pole? After finding the first pole, can we just ignore that one and then add all the other ones to see?
Not really.
No.
No, because what you're saying is that a time constant equals a pole. But see, that's not quite true, right? It's not just throwing out the lowest frequency time constant, and that's the lowest pole. It might be, but that's kind of where it's not quite valid. And usually what happens is this, and here's the real problem. A good design looks like this, will look like this. You'll have one very low frequency pole, and then a whole bunch of poles at the next spot. For your design now, a good design will be where all the poles are kind of lumped together. All right? Why is that? Because what's going to happen is this. As you look across your circuit, and you will find, wow, this pole is really low frequency. So you'll go in there, and you'll fix that pole up, okay? And you'll move it to a higher frequency by doing something like increasing the current that drives that node, reducing the resistance to it. Then what you'll no doubt find is another pole will start coming down to a lower frequency. Okay? Helping one will make another one worse. Okay? So you'll work on moving this one up, and then another one will start coming down. Okay? So you end up with a situation where you kind of have everything sort of clumped together is sort of the good design point. Okay? If one's really dominant all by itself, in the design you're doing now, not worry about the stability issue, then you probably could have done something with that one pole that's all by itself. Okay? It's going to be different when we do the stability problem, because I say we will take one pole and run it to a very low frequency and use that to kill the gain so that we can make the circuit stable. And so we will then have a whole bunch of poles at the second spot, right, or near the second place. But the lowest frequency pole will make artificially low. Okay? Yeah.
Why does the second pole move that way?
Why does it? Okay, I'm just kind of It doesn't always. I mean, it was just kind of Murphy's law, right? I mean, you would like to move the lowest frequency pole up, and you'd like the second pole to go even higher. Never works that way. It always comes lower, right? Always works against you. But let's maybe see if we can see this. Let's take this circuit. Okay. I'm not even sure if this is going to do it. Show it what I'm trying to show, but let's see if it does. Okay, so we have a C load here, right? And we have a V in, and here's going to some. This is some bias current that's setting the current through here. Now, first, let me say a couple things about this. First, what nodes do we need to worry about? Okay, we need to worry about this node because it has R0 in this direction, R0 in this direction. How about this node? Well, not really. It's being driven by a voltage source, so this is going to be at infinite resistance. How about this node? There's no signal on that node, right? This node right here, it sees 1 over GM to ground, and there's no signal there. So you don't have to worry about it, okay? Now, what about the capacitors we have to worry about? Well, there's a CGD. Let's call this transistor 2. Let's call this transistor 1. This is CGD of 2. For this node here, there's a CGD of 1. This is going to a ground, basically. Right? There's a CDB of 1, the drain to bulk from this one. There's going to be a CDB of 2, the drain to bulk of this transistor. Is that it? Let's see. There's a C load out here. I guess that's it for this node, right? Okay. So you can see there. So we still have to include this capacitor. Now, something you might have to watch out for in your design problem. Before, we didn't really care about what this bias current was, right? We said we could make it really low, okay? But what happens if you make it too low? What's going to happen in this circuit? Let's say I make this 1 picoamp of bias current. What's going to change in this circuit? See that? If I look at this circuit as it stands right now, let's look at CG2. Here's CG2, CGD2, okay? Okay, get it some other. Okay, this goes into, let me draw this a little bit. Okay, this is over here. Okay, this node here is a 1 over GM to ground, right? It's a diode connected transistor. This is diode ground. So this is supposed to be a 1 over GM, let's call this 3. GM3. If this current in this bias leg is really small, what's going to happen? 1 over GM3 could actually become fairly large, right? So you're going to have enough current going through this bias leg in order to make 1 over GM3 a small resistor, at least small in comparison to the resistors on this side, which are R0, right? So now you begin to see some of the constraints we have. Before we didn't care about the currents we used, but now we're going to have to begin to care about them. And the fact that we used 1 over GM is only small if there's enough current going through it. If it's getting to be a really small current, 1 over GM could be actually quite large. Right? Okay. All right. So let's go back to your question. So how would I make this let's say it's the output node. It's 1 over R02 in parallel with R01 times C load plus all this other capacitors. Let's call this plus C transistors. Okay, right? All the other things. CT is equal to CGD1 plus CGD2 plus CDB2 plus CDB1. Okay, so this is all these other parasitics. So this is like our dominant pole. This is our only pole in this circuit. Okay,
Professor.
Yep. gentleman, question?
I did. Okay. So is there CGD2? Do you assume it's to a capacitor to ground though?
Well, if 1 over GM is small, yeah, you can pretty much assume it's a ground, right? If this node here is megohms, okay, and this is 100 ohms, right? If I figure out the time constant for this capacitor, I'm going to do that, right? It's going to be a megohm plus 100 ohms, right? The 100 ohms is negligible, right?
So like 10 microamps is large.
Well, it's not the current so much; it's the resistance that you end up with the 1 over GM. So it's the size of this transistor as well, right? Right? GM's proportional to the W over L and the current, right? So you have to figure out so this is just becoming an issue here of what sets your current. Just make sure that size that transistor. You want to make it small, okay? Well, if you want to make it small because you don't want to waste much area, then you have to pump a lot of current through it in order to get enough 1 over GM. If you want to make it big, okay, then you have to have less current, but you're wasting power and you're having, but you get more area. So there's a little area power trade-off there. Okay. So how can I move this pole out? What can I do to this circuit? Okay, let's figure out some things we can do. So I should. So now there's a gain. There's a gain control right here. GM of 1 times R02 in parallel with R01. What am I doing here? Yeah. GM 1 times R02 in parallel with R01. So this is just right. A sub gain equals GM1 times R02 in parallel with R01. Okay, now you can see this. If I want lots of gain, I want this really large. What? Sorry. If I want lots of gain, I want R02 in parallel with R01 really large. If I make R02 in parallel with R01 really large, then my pole goes down to low frequency. So there's kind of an example of sort of making one thing better makes another thing worse. In fact, there's a really important result here. Notice if I take AG and multiply it times omega p, what do I end up? What does that come out to be? It's GM1 times R02 in parallel with R01 times 1 over R02 in parallel with R01 times CL plus CT. What happens here? These two resistances cancel out, okay? We end up with GM over CL plus CT. This is called the gain bandwidth product. Notice it's independent of the resistances. What happens if I cascoded this? Let's take that case. Let's jump to that case. Let's say I did a telescopic. So this is V bias 1, V bias 2, V bias 3. Here's V in. Here's V out. Okay, good old telescopic. What's the gain of this thing? Let's put a little C load out here. Gain of this thing is equal to GM of transistor 1, 2, 3, 4, times R out. Okay, R out of this node right here. And what's R out of this node right here? It's really big, right? It's going to be GM R out squared, right? Because of the cascoding on both sides, divided by 2, right? If GM and R outs are all the same, it'd be this value right there. Okay? So R out's really big, lots of gain. What's our pole at? What's the resistance driving this node, the CL? it's going to be that same R out, right? So the pole is going to be at 1 over R out times C load plus any other capacitance associated with that node. Let's say CL is much greater than all the other capacitors. I'll put it there, right? So if we do the gain bandwidth product, what happens? AG times omega P is equal to GM1 over CL plus CT. Didn't change. The gain went way up, right? The gain's really high. The gain here is GM R out quantity squared, right? That's what telescopic gives you. But the gain bandwidth product didn't change, so therefore what happened to the bandwidth? Went way down, right? So here's a really fundamental relationship you're going to find. Gain bandwidth products for a given topology, and this is a topology. Basically, we can increase the output resistance of this, but this basic circuit is going to end up with GM over the capacitance being the gain bandwidth product, and you're not going to be able to beat it. Okay? You're not going to be able to get better. You're not going to get, if you want more gain, you're going to lose in bandwidth. If you want more bandwidth, you're going to lose in gain. So you got to make a choice. And what you can do, if someone gives you a set of specifications, I want a gain of 200 million and I want a bandwidth of 1 gigahertz, you multiply those two numbers together, you figure out what the gain bandwidth product is, and you can sort of, what you can see right away, what you can do is there's a best case situation here. That's when we get rid of the CL. We're limited just by the transistor capacitances. Okay? You can see that you only can do so well with a given technology. A given ratio of GM to the capacitances of that transistor will limit how fast your circuit can be. Yeah.
How come the capacitances of the other transistors don't come into account because they're now in the signal path?
Which ones now?
I mean, like, so when you didn't have the cascode, you had,
These now will be the important ones. This will be the CT. It'll be this capacitance plus this capacitance will now become the C.
So, okay.
Let's call the CT for this circuit is going to be CGD2, CGD3, right? CDB2, CDB3, and CT is the sum of all those, right? This plus this plus this plus this.
Wouldn't that be different from your first circuit?
Yeah, but it's still the same kind of capacitance, CGD, CDB, and so on, right? So it's the same sort of capacitance, right? Now, what can you change? Some things you can change are W over L, right? Okay, so if I change if I make the W over L of this transistor really big, let's make this one really big, because I want a large GM. Okay? If I make GM really big, I make the W over L of this really big. So how do I do that? Well, I make the minimum size L, and I make a really big W. If I have a really big W, what's that going to do? This CDB is going to get really big, right? The drain capacitance on this node will get really large because they have a really big drain region. Okay. Also, the CGD1 will also get bigger when I make this transistor have a really big W over L. So both these capacitors will get a lot larger when I try to increase the W over L of this transistor to get more gain. So again, you sort of see this. There's a fairly fundamental relationship in these things that you end up with. Okay. Break time. 3 minutes. All right.
So in general, if you increase the W, would you lower this or increase it? It seems like a factor of 2 here, or kind of, so you'll probably, this thing will go down.
Now what happens? So let's increase W. Right. GM goes as the square root of W over L, right?
Right, square root, and then these guys go up by the
W.
Right. So that means this will go down.
This will get worse. Yeah, right.
Don't you want this as high as possible?
Yeah.
So you don't want it to W.
Go down.
I
Well, but you got it. But it turns out, there's other parasitics inside here. So what you won't end up is some W's will go down, some will go up, right, and so on and so on.
I do have a question though. Right here with the CGD two,
Mm-hmm.
right? You have the 1/GM right here.
Mm-hmm.
In the homework, we just let's say the W/L, all W was 2/0.18, right? And that's what, like 10, a little bit more than 10, right? And then it was 10 microamps going through here. I mean, was it okay? Because I think we just did. I mean, otherwise I don't know what else to do because I like the capacitance here. I just summed it up. It was a CGD1, or Miller. Well, this is actually to ground, so it's okay. CGD1 plus CGD2, like CGD1, I just added those up. But then it's not to ground here, it's actually to 1/GM3. So you can't really add that up, right? So what do you do in that case? You don't just add it up like capacity ground.
Well, you need to figure it out. I mean, in effect, actually what happens is, so, right, so you got this case, right? So you got a bunch of capacitors that are connected to ground,
Okay, yeah, yeah.
and you got one that's not,
Right?
right?
Yes.
It's connected to resistance. So the question is, what's the pole associated with this little network?
Right.
There's actually a pole zero thing going on here.
Pole zero?
There's a zero actually. There's a
Got
zero.
zero in there?
Yeah, yeah.
Okay, well, I don't.
So it's complicating things up, right?
Right.
So
You
yeah,
actually help on this one, 'cause I've been looking at it. I was like, wait, everyone else is taking this directly to ground, and I was like, wait, I don't think you can do that.
if that resistance here is much, much smaller than this one, then that zero's at such a high frequency, and it's probably a pretty good approximation to make this ground.
I'm not saying I don't want this to be as small as this. In that case, I'm asking you, what would I do if this
You're gonna have to work it out. You're gonna have to sort of
small
work it.
signal?
Just work this out. It's just an RC thing, right? Actual fact, if this gets larger, this capacitor becomes less important,
Okay. I
right?
don't even need to put that in there.
Yeah, so this capacitor actually gets less in size. I mean, it has less effect.
Why? I mean, the capacitance doesn't change. It's just,
If there's infinite resistance here, what would happen? It's a parallel combination, right? It's 1 over j omega c plus r, right? In this leg, right?
Right.
And it's 1 over j omega c in this leg, and so your parallel combination of all these things. Once this leg gets to be very large, it's unaffected by compared to these other ones.
Okay, but then the capacitance, I don't kind of know. I don't really know how to solve it. You're saying you just solve this circuit?
Yeah,
Wait a minute,
do it.
KVL?
Yeah. Do it once.
Huh?
Do it once.
To find the capacitance of this? 'Cause what we
Find,
need
find
is
the poles.
capacitance,
Find the poles and
right?
zeros of this. Find the poles and zeros of this.
But we just need to find the capacitance.
Right. Find the poles and zeros, and what you'll find is it'll be. I'm not exactly sure what it looks like. It'll be 1R of this guy, right, with C2 plus something or other, right? Probably some resistive I don't know.
Okay. So you can't just take all capacitances and sum them up and do that.
If this is really small,
You know, if it's big,
this big you can't.
you can't do it. Okay.
And I actually maybe choose this perhaps probably less, probably better. Yeah.
My report for the project.
Didn't come back.
It's really small.
Oh, okay. Because you emailed me and I was like,
I had it. I didn't give it to him. You turned it in class or something, right? Is that what happened?
I'm sorry?
You didn't turn it in late, right? You just turned it in class, right?
I told him late a week later.
A week late. Oh, 1 week late. Oh, okay.
And it's like 10% off, right?
Yeah.
On the gain bandwidth model.
Yeah. Yeah.
Do you have the slide or the paper that shows the diagram?
Which one?
How come the CL doesn't affect the gain?
No, I was just saying if you didn't have does it affect the gain,
Yeah.
low frequency gain.
Okay, so you're only doing low frequency gain. Right?
Yeah, when I say gain, low frequency gain. Yeah, right.
Well, how about in the homework then when we add the large capacitor, even if it's not low frequency gain, we assume that zeroes out gain. We had a huge capacitor.
That one has infinite gain, you mean? No, that one? That one has infinite low frequency gain?
It was earlier when we had
Oh, this one.
the load capacitor.
Oh, yeah, yeah, no.
Because it's a huge capacitor, we assume that it just basically zeroes out the gain.
Right.
When can you make that approximation? Like right
Zeroes out the
you can't
gain.
assume that, but
Well, it's at some frequency. At DC, it's still DC. The gain's still full gain, right?
okay.
It's only at we're trying to calculate with the pole location, so we make this approximation.
What you said about the last lecture, what about the value of CD or C mu or C gate? For,
Relative values.
yeah, for simplifying the circuits for some other
C
lecture.
gate. C gate is generally much bigger than CD. C mu. C mu is usually the smallest. CD is kind of second, and C gate's biggest by far.
And for the case like I don't have any C load here. I simulated the circuit and I got a pretty close value for my time calculation to the simulation, but
Good.
it's just for this code without CL. And I got the value about 100 mega, but the simulation is come to 800 mega.
100.
The second pole here.
Second pole here, probably.
No, the first pole is the lowest pole is here.
Oh, I see. This one
And
here.
the second pole here without the zero.
You got 100 versus 800.
Yeah, but the simulation is 800. I don't want to. What happened? Yeah. Is there anything you should consider in the simulation?
Make sure you calculate the capacitors right.
Because we had a very small value for the capacitors here, and with just the RO5 parallel with RO4.
The only thing I can say is maybe I would check the size of your capacitors and see how they compare to what Spice says, right?
But they should be pretty close because the other simulation came to the protocol cancel.
Either the capacitors or the resistance. There's only two things that can be off, right? So check the R out of this thing. Is that the same as the R outs that you get?
Is it important that I know that the value of the R out times CC is important, but for equation you said the last lectures, if the value which was important was, for example, C mu, which is we going to consider as a short circuit or something like that. Is it some other things for the when the
It's always R and C both. It's a combination of the two. Always look at that. You can't look at this one by himself because it's the relative position of the resistance of the pole location,
right
time
at the
constant.
moment we have a very big value for here,
Right.
R out times C, and for this point we have a very small value. So what should we do for this point? Is there anything going to be changed because of this other system?
No,
We
no.
shouldn't.
I think it's right. Check the capacitors. Check your output resistance. Make sure that's right.
Mm-hmm.
And check the capacitances, and you see if one of them somehow you calculated it wrong relative to what they did.
It's normally it's not acceptable for this.
You should be able to 20-30%. Okay. Okay. Let's just do some more examples. Okay. Let's take another case, very common case. Okay. And let's just analyze this a little bit. Let me make it easy to start with, and then I'll make it harder. Okay, so let's just make this to start with two current sources here biasing this differential pair, the loads for this differential pair with a good old, current source load down here, right? Okay, so what are the things we need to worry about here? So here's Vn plus and Vn minus. This is grounded. All right. So for common mode, for differential signals, okay, we can use our good old virtual. We talk about being a virtual ground. Okay, now there's certainly capacitance on this node, right? There's CGSs and there's a CDB of this guy right here. So there's lots of capacitance on this node. Okay. Now, What about for the differential mode case? Do we have to worry about a pole associated with this node? Yes? No? What? No, because it's virtual ground. Absolutely right. That's exactly right. So this is like a ground, right? It's like a ground. There's no signal changes on it. If there's no signal changes on it, then it's not having any effect on our frequency response. So therefore, we can, just like before, we can consider this to be a virtual. Being a virtual ground means it acts like a ground in terms of calculating our pole locations as well. Okay. So what's the answer going to be? So we can do the old half circuit analysis just like we did before for this, right? We'll have let's call this transistor 1, 2, 3, 4. So we can have, this is R01, the half circuit, right? You know, Vn differential over 2 going to a virtual ground, V out differential over 2. So we can find the poles of this thing just like we did for our inverter case, and it will be pretty much the same situation that we had before. Okay? Now, that's for differential. What about for common mode? So let's look at that. Let me just do it up here. So the common mode, I'll do it here. Let me just redraw it. So the common mode case, it's going to be R01, V in common, here's V out common. So we're doing the half circuit analysis here. And then we go down into R05. Okay, that's R. And to do our half circuit analysis, remember we make this twice as big, right? We take this, split it into two parts, so we have a 2R05 down here in the source. So this is our common mode half circuit. Now let's start putting the capacitors into this thing. Okay, there's a capacitor associated with, so let's start putting them in. So there's a CGD5, and there's plus a CDB5, the drain to bulk and gate to drain of this guy right here, right? So okay, so that's those two capacitors hanging off there. Then there's okay, then what else we have? Can I put them all in? Yeah, I don't need to label them all, right? But and then there's this R0 has some capacitance with it up too, so let me add that in. So there's a C, and this is going off to a diode connected transistor, let's say, right? So this capacitance here goes to 1 over GM to ground. So as long as 1 over GM is small compared to the output resistance of this node, this is like going to a virtual ground. If it gets too large, of course it's not. So this is at C, let's call this transistor 1. So this is C, no, it's transistor, this is 2. I guess this is 1 up here. So this is C, D, CGD 1 plus CDB 1. That's this capacitor right here, right? And here's the capacitor associated with transistor 2. All right. Okay, so that's all the stuff. Yeah.
Is that CDS?
CDB1, CGD1. Yeah, sorry. Okay. Now, so we need to work with this one out for the common mode gain. Let's well, yeah, it's a bad one. I think I want to do this. Let me simplify this a bit for a second. Let me go after this capacitance across this R0 down here, because that's the point I wanted to make. Okay. So it's, what is the big G sub m of this circuit? Low frequency. It's G sub m 2 over 1 plus GM2 times 2R05 in parallel with 1 over J omega CGD5 plus CDB5. I'm only including this capacitor right here, so let me not worry about all the rest of them here, okay, for a second. Okay? Just going to deal with this one. So this is another way you can sort of solve these things, right? You just take the low frequency, and it kind of shows you what's going to go on. I take the low frequency gain formula, I look and see where I have some extra impedances changing that result. And this CGS does something very different, right? Because it's kind of coupling between the gate and source here, so you have to handle that much more carefully. But right here, this capacitor is just in parallel with this resistor. So this resistor is in parallel with this set of capacitors. So now what's going to happen to the common mode gain? So just intuitively, can you see what's going to happen with common mode gain as we go up in frequency with this circuit, if we worry about this capacitor primarily? Who can tell me? It's going to increase. See what's going to happen? Because of this right here, this parallel, this impedance, this 1 over j omega c, as we go up in frequency, this will become a lower impedance value, which is kind of like a lower resistance, but the lower magnitude of impedance. This gets smaller. If we go to a very, very high frequency in the limit, this just shorts this out. So our common mode gain will go back to be the same as our differential mode gain. So you can see what's going to happen here. As we go up in frequency, our common mode rejection ratio is going to be reduced. It's going to start be less. Okay. Now, how does that happen? So let me just write this a little bit so I don't have so many variables. Let's call it GM times R0 in parallel with 1 over j omega c. Okay. Let's just work this out for a second, just to show where this stuff comes from. So this is GM over 1 plus GM times this parallel combination. So it's R0, 1 over j omega c over R0 plus 1 over j omega c. Okay. Okay. Let's multiply top and bottom by, let's multiply this by R0, or j omega c. Multiply top by j omega c, so I get GM over 1 plus GM R0 times 1 over 1 plus j omega R0c. Okay. Let's multiply top and bottom by 1 plus j omega R0c. So GM times 1 plus j omega R0c over 1 plus j omega R0c plus GM R0 right units there. Okay, equals, now I need to get this into the form that we always like, a 1 plus something or other, right? So how do I do that? Well, I need to divide by 1 plus GMR0, so let me do that. So I end up with, I have GM here, and I'm going to divide by a 1, factor out a 1 plus GMR0, and I'll end up with 1 plus j omega R0c over 1 plus j omega R0 over 1 plus GM R0 times c. Okay? And this is equal to, finally, GM over 1 plus GM R0 times 1 plus j omega R0c all over 1 plus j omega, and this is a parallel combination of R0 and 1 over GM. C. Okay? Is this right? Let's see here. Yeah, that's right. This is like GM01 plus GMRS, right? So this is the degeneration. This is the DC value, and it's the degeneration of the because we have R0 down here in the. I let R0 equal to 2R05 in case you're wondering how I got to here, right? So DC value. This is the old reduced value of the common mode gain. So this is ACM, right? Times we got a 0 and a pole, right? The 0, omega z, is at 1 over R0C. The pole is at 1 over R0 parallel with 1 over GM times C. Okay? So this is equal to GM over C approximately, right? Because 1 over GM is much smaller than R0. So what's going to happen to this circuit? What's going to happen is we're going to see this is clearly at a much higher frequency, right? You know, which is equal to 1 over GM times C. In other words, look at that. So the resistance of this pole is at a much higher frequency. So the 0 is at a much lower frequency. So we're going to start plotting our common mode gain. What's going to happen? It's going to start off, and at the 0, which is at 1 over omega z, the common mode gain is going to start increasing until we get up to the pole, which is at omega p, and then it'll flatten out. And it'll flatten out at this value here of GM over, well, I guess what does it flatten out at? It flattens out at 1, I guess. So we can see where it flattens out. Plug into here, let omega be very large, okay? So that the 1's go away. This actually, GM over 1 plus GMR0 is, well, you can figure it out. Should I figure it out? Yeah, I'll figure it out. GM over 1 plus GMR0. At very high frequency, this will be equal to R0C, J omega R0C over J omega R0 parallel with 1 over GM-C. Well, the C's cancel, the J omegas cancel. So I end up with GM R0 over 1 plus GM R0 times R0 over 1 plus GM R0 . All right, so this cancels with this. R0 cancels with this. This got the wrong units. This is GM or something like that. This is GM. This is big GM. Big GM common mode, right? So it ends up being, so this is times R out, right? So this is all, this should be times R out. Times R out. So we end up, this thing goes up to GM times R out, and it starts off as GM over 1 plus GM R0 times R out. So it starts out with the really low value, and then it goes up to be just GMR out, which is actually the gain of the differential mode gain. So we have no common mode gain at the scope high frequency. Okay? So just little word of the wise here. When you start doing your differential pair circuits, you're going to begin to see this problem. Now, what about, let's take another case. Let's take another circuit that we know and love. Let me take this one. Okay, our good old current source load thing. Here's V in plus, V in minus, V out. Okay, how do we analyze this one? What can you think? What's going to happen on this circuit? Remember, we basically get gain from two sides, right? We get gain from this side, and we get gain from this side to the output, right? The way we get gain from this side to the output is we have a voltage change that gives us a current here, which is mirrored over here, and then finally gets into this output. So what do we have to worry about? There's capacitance on this node on this side. So you're going to begin to see this is at a fairly, and the time constant here is really relatively, it's 1 over GM for this resistor right here. So this kind of current division that we're going to see, effectively what's going to happen is this current here, some of it's going to start going into the capacitor, and instead of going into this transistor right here, okay? And effectively what will happen is we'll have less current being mirrored over here coming to our output. Now, that's very different than what's happening on this other side, right? There's no such issue at all here. This current is generated here and it comes right to our output. Let's say I have a C load here, so it's going to come right out of our output node. So these two sides act very differently with respect to high frequency response. And in effect what happens is there's a zero created on this side here. Okay, the mismatch, when you have a mismatch of two sides like this, in fact, if we did something like, let's say we put a resistor on the one side of this differential pair, for whatever reason, this is just academic, just put a parallel resistor over there. So we mismatched these two sides. Just to tell you what happens is, the result will be, actually this will create a zero. It creates a pole zero pair, okay? You call these doublets. When you have this mismatch of two sides, you get a doublet. Okay, it's a pole zero pair, which kind of has adds a little bit of weirdness to your whole design. Maybe we should do a homework problem that will do this for you. Where this becomes really important, where do we have important poles being created that are different? Think about our folded cascode circuit, right? When you fold that thing over, right, you got a bunch of extra nodes sitting inside that where that folding's happening, right? That's different on the two sides there, so you get a fairly complex pole and zero combination going on there for this, the high order poles and zeros. The lowest pole will probably be at the output. The lowest pole will be right here. But the next high order stuff that we have to worry about in this, there's combinations of poles and zeros we have to sort of begin to worry about. Okay? So just fair warning. When you start seeing poles and zeros show up in your, yeah.
Can you explain why a pair of zero poles?
Why it shows up? Yeah. It has to do with this. How can I show this quickly? It's like, okay, so let's say V out. Let me just try this. It's V in differential over 2 times a transfer function, 1 plus J omega over omega P1. Can you buy this? Plus V in differential over 2 times 1 over 1 plus J omega over omega P2. In other words, when I go from the transfer function from each of these inputs to the output, okay? Oops, sorry. When I go from the transfer each of these inputs to the output, let's say this is V in differential over 2 and this is minus V in differential over 2, but the polarities, the signs get changed. So if we had the same poles, this thing would end up V out would be equal to, times some gain, right? A0 times A0. V out would be equal to V input differential times A0 over 1 plus J omega over omega P1. Okay, right? But now let's say because of this mismatch business we have here, we have two different poles that are slightly different from each other. So our transfer function to the output is from one side is associated with pole 1, so to the other side is associated with pole 2. Okay? By that? See what I'm doing there? Now, let's take it's actually, I should have a minus sign here somewhere. And that's, let me just conceptually here, right? We can do this more accurately next time. But to answer your question, how does a 0 come up? If it's basically you're taking the difference of two transfer functions. There should be a differencing going on here, right? And this should be minus here. I'm not quite sure how that works out. But if we take the difference of two transfer functions to get to this current that comes into the output, what do you end up with here? You see that this will be 1 plus j omega over omega p2 minus 1 plus j omega over omega p1 over the product of these two things, right? Well, this has a different gain. This is a0 and this is a1, I guess. I guess you can sort of see, we subtract these two things off, right? You get an a0 here and you get an a1 here, right? And you'll see that like you get, the top is a0 minus a1 plus, a0 times j omega over omega p2 and plus and so on. You can sort of see there's a 0, a real and imaginary part. So there's a 0 being formed in that numerator. I'll do that better next time. Basically, if you have mismatches of differential pairs, you create zeros, and I'll show you better next time how to do that. Okay.
What if the mismatch is like from a process? Is that 0 come down low enough?
It's a pole 0 pair. So it's kind of, if it gets small, then it's just a little doublet that happens, right? And they kind of it compensates out as soon as you get far away from it, right? So, but it can. Yeah, I mean, process variations are another place where you get some trouble there. It's just, and since it's not a very big error, generally in the process, it's not a big split, right? So. Yes.
Do you remember in the office hour I talked to you about the game